Hey, Math 7 students. So we are jumping into our final topic of the year. So this will be our probability section. So we are almost done, just a little bit more to go. So I'm going to be kind of looking at the real important starts of probability, and we'll round the year off with that. So a few just kind of learning goals. What we're going to try to do in this video is, one, we want to make sure that we know kind of how to state probabilities and state if they're likely or unlikely. So we'll kind of do a super quick review of some Math 6 probability stuff to kind of jump us into this topic. Then we're going to introduce some new stuff, so probability notation, how to look at that and make that, and then use it. And then finally, how to look at some more complex probabilities. So we're going into how to calculate a 2-dice roll. So can I make a probability table if I've got some kind of event that relies on 2 sub-events? And what I mean by those 2 sub-events is a good example of that. If I've got 2 dice to roll, I've got the event of 1 dice and the event of 2 dice. So we'll look how to calculate that as well. So first off, super quick math review if you see some probabilities thrown at you. So you can get something like impossible. It's like if I have a probability of 0, or we can even do it as percent as well. We've got certain over here. That's like a probability of 1, or 100%. It's percentage equivalent. And then we also got what we likely in just our everyday language call a coin flip. That's just a 1/2 or 50% probability. And so anything between 0 and 50% we classify as unlikely. So for instance, if I said we've got a 10% or 1 in 10 chance that it'll rain tomorrow, you'll probably say that's pretty unlikely. Where the forecaster said, well, we've got a 75% chance or 3 out of 4 probability, then you might say that's a very likely probability of that happening. So it'll happen more times than not, less times than not, and then we've got our kind of certains, uncertains, impossibles, and our 50/50s. So on that, let's jump in. So our first problem that we're going to look at is one that you should have already done because it was our task for Friday. So if you haven't done this problem yet with Jared trying to figure out if he can win a game, pause this video. You don't even have to go to the Schoology page. You can just do it from looking at it here. But we've got Jared, and he's going to see how probable is it for him to win. So we can choose one of 8 boxes to win a prize. So you see the boxes in front of you, and then we see a description of what's in the boxes. So one of the boxes has a big prize, 3 of the boxes have a medium prize, 3 of the boxes have a smaller prize, and 1 box is sadly empty. So we want to gauge how confident Jared should be. So we're going to try to do this just with an introductory kind of little probability, and also to introduce probability notation. So let's just start out, let's draw all of our boxes. So we got 8 of them. So I'm just going to draw a 4x2 rectangle. We'll do a line down the middle, and then 3 dashes down the middle, just to say Jared is going to choose one of these boxes. So let's label what we have. So we've got the big prize, label that as BP. We've got 3 medium prizes, so I'll write that as MP, MP, MP. We've got 3 smaller prizes, and we have 1 that is empty. So essentially we have 8 outcomes, and I'll go ahead and highlight the ones that are winners. So if he chooses any of these boxes that I've highlighted in red, he essentially wins a prize. So a lot of you probably said, well, that is a 7 out of 8 or 87.5% probability if you do the ratio 1 in 8. But I want to introduce some probability notation, how you would do this. So you'll see this later on in math classes, but essentially we've got this weird notation. We got P parentheses outcome equals the ratio of number of favorable outcomes to the number of total outcomes. So the way you read this P parentheses outcome, P, I mean, you can think of that as probability. So probability of, we'll say that outcome right there. So whatever's inside the parentheses is the outcome you are looking for. So if I were to do this problem right here, I would say, well, how certain will he be to win a prize? So that's the probability of winning. And now we just take the number of favorable outcomes, and what I mean is favorable towards this specific outcome. So we've got 1, 2, 3, 4, 5, 6, 7 favorable outcomes, outcomes that favor a win, out of 1, 2, 3, 4, 5, 6, 7, 8 total outcomes. So we could say it's a 7 out of 8 chance, or if you wanted to convert that to a percentage, an 87.5% chance, which I would say that's very likely. All right, so let's jump in a little more complex now. So we're going to look at that problem that we did during the office hours last week. We did the great soda bet. So we're going to look at dice rolls. So now we're going to kind of up the difficulty a little bit. So essentially, we're going to look at that great soda bet problem where I had 2 dice. So we could say I've got dice number 1 and dice number 2, and I very purposely made these different colors so you can really differentiate. There is a outcome of the first dice sort of rolling onto one number and the outcome of the second dice, and those are 2 distinct events. You can't really mesh them together. And so we're going to look at why did I choose the numbers 6, 7, and 8 in this game. So remember, in this game it was just a basic 2 dice roll where you sum them together at the end. So 1 and 4 make 5. If I roll a 6 and a 2, that makes 8. So we're going to look at calculating some more complex probability. So I'm going to start just by taking 1 dice. So if I were to take 1 dice, it would not be that hard to sort of list out all the outcomes. So the probability of the first dice, you've got, well, I could roll a 1, a 2, a 3, a 4, a 5, and a 6. And I could very easily calculate the probabilities of this. I could say, well, probability of rolling a 1 is 1 in 6, probability of rolling a 2 is 1 in 6, the probability of 3 is 1 in 6. They're all 1 in 6 probabilities. But what happens if I have to take 2 together? So we're going to say this top column is dice number 1. And we're going to say this second dice is dice number 2, and we're going to make a probability table for this. So I've got dice number 1, that'll be in red, and I've got dice number 2, that'll be in blue. And I could roll a 1, 2, 3, 4, 5, and 6. And you'll notice I made these 2 different dimensions because they're completely different outcomes. What dice 1 rolls does not depend on what dice 2 rolls at all. They don't really affect each other. So we could say I could roll, and this will be your kind of way of tracking each possible outcomes, because I could roll 1 through 6 on the blue dice and 1 through 6 on the red dice, and we got to track every single individual outcome. So we're going to look at the probabilities of why I chose 6, 7, and 8. So we're just going to list out our outcomes. So we can start here. I could roll a 1 and a 1. That's a 2. I could roll a 1 on the blue dice, a 2 on the red dice. That's 3. 1 and 3. That's a 4. And for the rest of these, I'm going to quickly fill these in. So we got 5, 6, 7. 2 and 1 make 3, 4, 5, 6, 7, 8. 3 and 1 make 4, and we just descend up again. 4 and 1 make 5. We got 5 and 1 makes 6. 6 and 1 makes 7. And we've got our table filled out. So once you kind of know the pattern, it's actually pretty quick to make these. But we've got our table filled out. And as you can see, if I were to try and find the probability of, let's say, probability of 7, all I would do is I would look around this table and I say, well, I've got 36 possibilities and 1, 2, 3, 4, 5, 6 possible rolls of 7. So I could say that using that notation from earlier, I've got the probability of 7. Well, there's 6 ways to make 7 out of 36 total ways, which I can say, if I reduce that down, that's a 1 in 6 chance. And I could do the same with any of these. So I could say, well, what's the probability of rolling a 6? If I want the probability of rolling a 6, I could just count out how many times can I roll a 6 out of these 36 outcomes. Well, it's 5 different ways to roll a 6. So I say the probability of rolling a 6 is just 5 out of 36. And I can do the same with any of these. Let's take a look at one of the rolls you guys got, because I believe I gave you guys 3, 4, 10, and 11. And I could calculate the probability of rolling 3, and we can see, well, there's only, let me fix my little drawing tool real quick. There's only 2 possible ways to roll a 3. So the probability of a 3 is just a 2 out of 36, or 1 out of 18 rolls. So you can see probability of rolling a 7, far, far, far likelier. I'll roll a 7 approximately 1 out of every 6 tries. Probability of rolling a 3, 1 out of every 18 tries. I could calculate every single one of these 11 outcomes 2 through 12. So now we're going to look at one more tiny thing, which is how would I use these probabilities to make predictions? So we're going to answer 2 separate questions. So first, how many 7s would I expect out of 500 rolls? So I'm going to start with that probability that I calculated for 7. So I know the probability of rolling a 7 is 1 out of 6 outcomes. So I'll take P of 7 is 1 out of 6. And then I'm just going to say, well, that's out of 1 out of every 6 outcomes. I'm looking for how many 7s out of 500 outcomes. So to do this, we're just looking back to unit 2, which was equivalent ratio. So all I need to do, solve for that missing unknown. So we'll just try a little X there to say that's our unknown, that's what we're trying to solve for. So I can move left to right. I can move up and down, just like we learned with proportional relationships. If I see a 1 and a 6, that's a really easy operation right there. So multiply 6, which means I can go the opposite way to get to my X. Let's divide by 6, and I've got the number of 7s in 500 rolls is equal to 500 divided by 6, which if I were to do that math, you could do it on your own, but I get that X is, and let's just put it right where it is, 83.3 repeated. So to state this, I know I wouldn't expect 83 and 1/3 7s. I would expect a whole number. So we would just say approximately 83 7s rolled. And that would be kind of what we'd expected. And that's why we say theoretical. So when we say theoretical, it's basically what's the expected probability? What do we expect? So we expect approximately 83 7s rolled. So let's do one more. Let's do how many 3s. So we'll pop back here real quick. We need our probability for 3. We could use 2 out of 36, but 1 out of 18 is a little cleaner, so let's use that. So let's start with probability of 3. That's equal to 1 out of 18 rolls. So now we just do the same kind of math. I don't want how many out of 18. I want how many out of 500. So same basic steps. We've got some easy operations up and down. Of course, I could move left and right, but I'd have to do some 500 divided by 18. Let's move up and down instead because we got those nice clean numbers. So multiply by 18, which means I can do the opposite operation to go the other way. Divide by 18. And if I pull this out and do 500 divided by 18, that gives me 27.7 repeated. And let's round to the nearest whole number because I know I can't do a decimal roll. So we'd expect approximately, our approximately symbol, approximately 28 3s rolled. So hopefully that made a ton of sense. If it didn't, make sure you bring your questions to office hours that we'll have on Wednesday. So I hope you all have an excellent week. Take care.